Is it recording? Yes, it is. Though apparently now to the cloud, whatever, who cares? Pen, please work. All right, so 4xy plus 1. All right, so we compute the gradient of this thing, right? Again, I hope Aziz sort of did this for you. So minus 4y and then 4y cubed minus 4x. And this has to be equal to 0, 0. So this gives us two equations, two unknowns. But generally, these things could be, right? You generally will have n equations and n unknowns, and you have to solve them, and you'll have, a nonlinear system of equations, which is just one thing that we might have to solve, and it becomes a little bit more complicated. But that's fine if we want to solve this. So we'd set, okay, let's look at the first equation. Let's maybe number these equations. So we get y is equal to x cubed from 1. And then if I go and I plug that into equation 2, what am I going to get? So I'm going to get x cubed minus x. That's equal to x to the 9 minus x. This whole thing has to be equal to 0. That's equal to what? X to the 8 minus 1. And if we factor that, what do we get? So we get x squared minus 1, x squared plus 1 times x to the 4. Here, let me put that on a new line. X. My pen is still acting up. X minus 1, x plus 1, x squared plus 1, x to the 4 plus 1, like that. These two things are never equal to 0. So this tells us that x can be either 0 or plus or minus 1. And then if we then use this equation again, y is equal to x cubed, then, so if y equals x cubed, then we get these solutions. So we get 0, 0, 1, 1, and negative 1, negative 1, right? And that was B. So that's how we sort that out. Okay. Any questions about that? Oh, why didn't I use the 4? I mean, the 4 is there. I just kind of got rid of it. So it really should be 4x cubed minus 4y is equal to 0. But, right, like the 4 there is just going to vanish, right? Like I can divide both sides of the equation by 4, and then the 4 goes away. So the 4 is there. It's just because there was a 4 in both terms, I didn't really need it. So I just got rid of it. Okay, thanks for the reminder. Is everyone good then? Does that make sense? Generally, it is sort of, if you want more practice with these things, it's sort of hard. These ones are actually pretty hard to create yourself. I would strongly suggest, you Google multi-variable critical points or something like that. There's a couple in the book, obviously. But if you really, this is, again, a fairly standard thing in multivariate calculus. So if you do want to, get more practice beyond what even the book has, then it's fairly easy to Google, multivariate critical points, and you'll get lots of examples of doing this sort of stuff. Okay, otherwise we can move into office hours here. So I've got a couple questions in my queue already, but I just want to make sure there aren't any other questions about this. So if there are any other questions about this, please yell, and we can do it. Kelly, sure. Yeah, so Christian, exactly. If there's more variables, like there is x, y, and a z, you'll definitely have 3 equations and 3 unknowns, and you have to again go through some sort of similar process. The sort of problem when you have nonlinear systems of equations is that there isn't like an algorithm for solving those systems. You kind of just have to play around with things until you figure it out. Yeah, I see it. Okay, cool. All right, let's get started here. So I got asked about assignment 11, question 1. Now the solutions are up, but I presume that there's still some confusion about that. So let me just pull it up here so I have it in front of me. Yeah, Jordan, that's actually a really hard question. That's I kind of bring it up as like a math interest thing. But the reason is that basically the thing that you would get is just too big. It's just too big to be a set. And understanding why that's true requires a little bit of like nasty logic-y sort of stuff. So that requires we talk about Russell's paradox and self-referential paradoxes and stuff like this. So it's a little bit beyond the scope of our course. If I get all these questions out of the way, though, I'll talk to you more about it because it is super fun. But let me do this stuff first. It is very interesting. Okay, so so for question one, we ended up doing a bunch of these over the week, right? Because we did a bunch of them as we were running up to it. Let me maybe just do one of these questions because like I said, we've already, I did a bunch of them in previous office hours. So you know what? Let me get the graph here. I should have brought it up on this computer because I need the graph. This computer's running slow for some reason. Don't do it. Okay. Oh, you know why? It's because it's trying to render the video before it canceled out as well. So it's doing a bunch of stuff at once. All right, here, let me get the graph. Just about have it. Okay. So we have this thing, and again, let's try question 2, like part 2. So this is Q1 part 2. And again, like check last week's Thursday and Tuesday office hours because we did a bunch of them there as well. So this one asked for the integral from 0 to 1 of f of x minus g of x, right? Dx. And probably what you want to do is, you can break this into 2 parts. So let's maybe just look at, I guess I want to keep the graph on the screen. So let's just look at this one, okay? Because if we can do f of x, then g of x is going to follow the same sort of way. And the way that we want to do this is by substitution. So what we're going to do is we're going to say let u be capital F, right? That means the du is f prime of x dx. But by definition, capital F is an antiderivative of little f, right? So that's going to be f of x dx. So when I do substitution, I'm going to leave the boundaries, the upper and lower bounds of integration. I'm going to leave those deliberately blank for now because we're going to have to figure out what those are. So that's going to give me u du, but I got to figure out, what these things are right here. Okay. So in order to figure those out, right, I plug 0 into u. So I'm going to f of 0. And that's the integral from -2 to 0, f of t dt. So to figure that out, I'm going to go to my graph here, and I'm going to look at what is the area between -2 and 2. And that's going to be this thing, right? And those areas are equal, and they cancel each other out, right? So this number is just equal to 0 without sort of doing any computation. That's kind of nice. Okay, for the other one, which is what u, here, I can just put that in here now. So u of 1 is f of 1. So that's the integral from -2 to 1, f of t dt. And when I do that, so that's just going to add on this thing right here. So again, I still get 0, right, from -2 to 0. Those two things still cancel out. But now I get this rectangle here. And this rectangle has a width of 1 and a height of 1, but it's beneath the x-axis. So it has actually a negative area. Right? -1 like that. Okay. And now I can find an antiderivative for u, right? I know what that is. 1/2 u squared from 0 to -1. So I'm going to get 1/2 times -1 squared. So I get 1/2 like that. Okay. And so that's just first half, right? That's f, capital F times little f. Now, capital G times little g is basically the exact same sort of thing, but you're going to have to do a different substitution. And again, you're going to have to figure out, what capital G of 0 is and what capital G of 1 is, and these sorts of things. But it's still the exact same type of substitution, right? It's effectively the same problem. Problem 3 is also the exact same substitution. It's basically exactly the substitution. And we realized, so 3 is the same thing, right? So 3 is you have the integral g prime f of x dx. So again, if you let u be capital F, du is, well, let's just go to that. It's the exact same substitution, right? And so now you get the integral g prime u times u du, right? And again, you have to figure out, what are these things? But you do it the exact same way. You just look at the graph and you add up the areas. And it turns out we actually sort of made a mistake when we made this problem. This integral immediately ends up being 0. So if you actually compute what these are, they're the same number. And so you just get 0. But the original intent was actually for you to do an integration by parts on this. Oh, you know what? Maybe I should use a different variable. I should use y here. So I don't have to reuse u. So let's change these to y's. Now it's a y substitution instead of a u substitution. I don't like how that looks. Let me just rewrite it. Right, and then you would do a substitution. U is equal to y. dv is g prime of y. du is dy. And then you integrate by parts. Right, so you're going to get uv minus the integral of v du. Right, and again, you can integrate, you can evaluate, you have to figure out what the bounds are, but that is just the function big G, so you can compute it by looking at the graph. Wouldn't the derivative of u be u prime? Like, in what sense? So the derivative of u with respect to u is 1, right? In the second last one, it's y now. What, like right here? Is that like the integral of g prime of y? Yeah, I don't quite see what you're saying. So do you agree? Are you happy with this, or do you still have objection with this? This is good, and it's the next line, or maybe let me write this clearer. Maybe I just wrote too quick. Yeah, I'm integrating by parts. Yeah, right, because that's the sort of thing when you get like a y times a function or an x times a function. Right, yeah, but this is parts, so it's a slightly different computation. Okay, and yeah, so for those of you, again, you're still a little bit stuck on that, you can go back, you can check it out. Tuesday and Thursday of last week, we did a bunch of these in the office hours as well for like 8-28, 8-29, we did a bunch of those, so. Finding antiderivatives of fractions, maybe we can 8.1 B and D. Okay, let me put that on the list. All right. The next one up was 824. So 8-24 rather. What is this? What the heck? Okay, there we go. So 8-24. Gotta go through my notes and find it. All right, 824. Sure, I feel like I did do this one in class one day. Does anyone remember what day I did 824 in? Did I do it? Because I seem to recall having done it in class. Let me get the graph again. Oh, this is page 243. It was different? Okay. I'll trust you. All right, here, I got the graph. So here's 824. Okay, so question one, determine the, oh, you know what? We did a poll question like this, right? Which is what it was. So we define capital G to be the integral from 1 to x of this function, right? F of s ds. And then it says determine the intervals where G prime is greater than 0, determine the inflection points, and find the absolute max and min. Yeah. Okay. So where is, so question one, or part A, is we want G prime of x to be greater than or equal to 0. So who can tell me where, just based off of, looking at the graph, where is G prime of x greater than or equal to 0? This was actually a test question one year too. That's where this comes from. Okay, so the graph is the graph of f, right? Maybe I should have written that in. Yeah, exactly. Right? So here, let me just maybe put that in quickly. So here's the graph of y equals f of x. So the answer here, right, G prime of x, oops, let's not use black. So we know that G prime of x is equal to f of x, and we want to know where f of x is greater than or equal to 0. Well, that to me looks like from 0 to a half, and then from 2 to 4, right? One half union 2 to 4, like that, right? Yep. Everyone see that? Is everyone okay with it? But it starts at, yeah, when x is less than 1, that's true. Hold on, let's reason this out a bit. This is a good point. This is a good point. Let's double check, because what do we do when x is less than 1? So when x is, ooh, is this gonna do something? So the problem is that the integral starts at 1, right? Not at 0. So we just need to be careful about the signs, because it actually could be 1/2 to 1, right? Because if we invert that, it's going to do something different. Okay, so if you're not certain, let's double check it. I think you're right. I think it does, right? Like FTC isn't going to care. And that is a perfectly valid point. The FTC does not care what that bottom bound of integration is, right? So it should still be 0 to a half. Now, For any of you who aren't certain, how do you check this on a test? Like, let's say it comes up on a test and you're like, wait a second, the FTC says that lower bound of integration shouldn't matter, but I know that I'm integrating backwards. How could you double check your answer here? What would you do? Well, no, because it doesn't say, like, this function is still defined. So the direct message I just got is if the interval starts at 1, basically, do we ignore, right? Like, I assume that's what you're saying, direct message, or like, do we ignore what happens before 1? And the answer is no, you still can define g of 0, right? Like g of 0 still makes sense because that would be the integral from 1 to 0. And we know how to deal with that, right? Like that's the negative integral from 0 to 1. ds, right? Yeah. Sure, posting it on Piazza is a way that you could deal with it. So just because the integral though starts at 1 doesn't mean you can ignore the stuff that happens behind it, right? So you do still have to worry about that stuff. Yeah. Okay. FTC still says it would work. Now, if you don't know, that portion from 0 to 1 is just a line, right? Like we know exactly what the equation of this line is. So if you're really not certain, you actually can break this down a little bit further and you can say, listen, the equation of the line here is what? This to me looks like y is equal to 1 minus 2x, right? Does that work out? Right? X is 0, that gives me 1. When x is equal to 1, that's equal to negative 1. And so you know explicitly what the function is on the interval 0 to 1, right? So you can actually just plug that in. But FTC says that actually shouldn't make a difference, and you should still get 0 to 1/2. Okay, but you can double check it by actually plugging the numbers in there. Okay, so B is find the inflection points, right? Well, because you actually know what the function is then, right? You can literally compute it, like g of, so let's say on 0, 1, g of x is that function, right? And you can just explicitly compute that because you know how to find an antiderivative of 1 minus 2x. So the idea is that you don't want to use a piecewise function to define the integral of this function on the entire thing, right? Like that's really, really messy. But in something like this, if you're not certain how that function is behaving on that little slice, you can actually just, you know what the equation of that line is. So you can just plug it into the integral and figure out what the answer is, right? Okay, so inflection points are where the second derivative is equal to 0. Stupid. Okay, there, pen. Stay alive. Okay, so G double prime. So it's where the concavity is going to switch, but in particular where the second derivative is equal to 0 or it does not exist, right? So if I look at the graph, where does the second derivative equal 0 or does not exist? Since it's negative on and positive on each half, could you break? Yeah, absolutely. 0 to, what do you mean 1.5? Do you just mean 0.5? Zero to 1.5, but 1.5 is like over here. Yeah, 0.5. Okay, yeah, just making sure. Yes, yeah, that's totally fine. You could do that. Okay, so when you all look at this graph, where does the second derivative of g equal 0? Now, or does not exist. Now, remember, the first derivative of g is f, right? So the second derivative of g is f prime. So if you look at this graph, where is the second derivative either does not exist or is equal to 0? One and 3 and 4, but why do you include 4 and not 2 then? Right, yeah, exactly. 1, 2, 3, and 4. So what we're looking for is the derivative of f right? And f is the function actually graphed here. So the function is not differentiable here, here, and here because it has cusps there, right? And so that's where f prime does not exist. Right? Does not exist, does not exist. And then the other thing is, where is the derivative equal to 0? And the only place where you have that like horizontal tangent is right here, right? So here you get f prime of x is equal to 0. Yeah. Yeah, or where the derivative doesn't exist. Inflection point is where concavity changes, right? But we're asking for the concavity change of capital G. And so where the second derivative of capital G is changing, we're asking where, that's the equivalent of saying, where does the first derivative of f change, right? So it's just sort of like we've obfuscated which derivative we're asking about. Yeah, exactly. Sharp turns or do not exist. Yeah, absolutely. Okay, so those are our potential inflection points. Now, can basically, I guess what I want to say here, where, for which ones is the concavity actually changing though? Yeah, exactly. Yeah, horizontal. Yeah. So for which of these does the concavity actually change? Okay, so these are all the places where the second derivative is 0, does not exist, but for which of these, because an inflection is strictly speaking where the concavity changes. Yeah, right. Yeah, 1 and hold on, let me double check this. Yes, 1 and 3. Yeah. Right? Because what you're going to do is you're going to look at the signs of f prime on either side. And so to the left, f prime or g double prime is negative, and to the right, it's positive. So it is actually changing concavity at 1, and it's changing concavity at 3, but it's not changing concavity at 2 and 4. Right, exactly. Yeah, you can have concavity changes at cusps. And the thing is, if you were to actually plot G is smooth. G is totally differentiable everywhere. So like those cusps actually just sort of disappear when you integrate those things out, right? So 1 and 3 are the actual inflection points. Okay. Yeah, I don't know. I think it's harder. It might be harder than term test 5, but I don't think it's like brutal. But integration is a little bit tougher. Well, A11 is kind of weird, right? Because it was sort of like simultaneously review, but also brand new for almost everyone. So it's harder to say. Like it's hard for me to say how it is relative to that. And assignments and tests are different, right? It is it's sort of like on par with that, with the question 1 of A11, right? It's sort of like on par with what we're doing right now. Yeah, the last part of the homogeneous function thing was hard for sure, but we wanted to give you one that was a little bit tough. I'd say so. I'd say it was similar to other stuff. Yeah. Right. I think we've been pretty consistent all year. So, I mean, it's the 6th term test, and by now you've probably got a feeling for the sorts of things we ask, right? No, I think we're going to be in person unless something crazy happens, right? The plan right now is to be in person unless, the world comes to an end, sort of thing. Yeah, I don't know. I mean, it's too early to say, right? Anything could happen. Anything could happen. Now, the final part of this question is a little bit nasty. So it says find the absolute maximum and minimum of G. And like for the most part, what you're going to be looking for is, you're going to look for, if we go back up here, so we know that maxes and mins have to occur at critical points. So where are the critical points of this function of capital G? Where are the critical points? Those are the critical points of f, but not the critical points of G, right? G is the integral. So it's the same, it's very similar to like this, right? So g prime of x is equal to f of x is equal to 0 or does not exist. So where does the function f equal 0 or does not exist? Anyone? Oh, okay. Yeah, 2, 4, definitely. These are critical points. There's also a half here. Ariana, I like 0. You're right. 0 is technically an answer. But then if you're going to include 0, you should also include 6. Oh, you did include 6. Yeah, 100%. So yeah, you could include those as well. And you're right. You have to, kind of want to include your endpoints anyway. So yeah, I would say that's totally a fair answer. And what you want to do now is you can use a second or a first derivative test to figure out which are local maxima and which are local minima. But sort of it doesn't end up being worth doing because because the question is asking you for global maxima and minima anyway, you just have to unfortunately compute what G is at each of these numbers, right? So there's some work to be done there. Right? So you can go through and you can be like, oh, G of 1 looks like it's a quarter. Or sorry, G of a half is a quarter. I don't know why I wrote 14 and 1. So G of a half is equal to a quarter. G of 2 is negative 1/2. G of 4, or I guess that's, this is G of negative a half, right? Anyway, whatever, you keep going and you just keep on adding up the areas and you figure out what everything is and you compute your global max and min, right? It's not that it equals 0, it's that it doesn't, it's that f doesn't, I think Ariana was basically just including the endpoints there, but strictly speaking, f, like, yeah, it's not that f is equal to 0 there. It's that just to include the endpoints as potential places where your function could be a max or min anyway. So you guys are right. It's not that those are strictly speaking critical points, but it was just a matter of including the endpoints. But you're right. You're right. So I've maybe confused things more. The only critical points are 1/2, 2, and 4, but we're going to include 0 and 6 when we check our answer because we know that those are potential maxima and minima anyway. Yeah, so that's what Ariana was doing. It was endpoints and critical points, but you're all right as well that the critical points don't include the endpoints in this case. So just to clarify that, right? So it's not confusing. Okay. Am I teaching in the summer? No, I'm not teaching in the summer. I always take the summers off. I mean, not off, right? I just do my own stuff in the summer, but teaching all year just gets me so burnt out. I need to do my own stuff. Okay, let's look at 820. I think was the next one. Ooh, this is a really fun one. This was an assignment one year, 8-20. So I've given you f of x is equal to e to the x plus e to the negative x over 2. G of x is e to the x minus e to the negative x divided by 2. Okay, and we're given that this is true, and this stuff is true from like previous exercises, so you can just assume it. G of x squared is equal to 1. And then it says find the integral of f of x to the 4 g of x to the 5 dx. All right. Okay, so this is this problem. This is an assignment problem. Yeah. It was an assignment problem one year. It is a fun question. Students definitely struggled on it, but that's okay. It's okay to struggle on things sometimes. The key trick here is, you're probably going to need a substitution. And if you let u be f of x, then du is going to be g of x, right? And on the other hand, you could also let u be g of x. And if that's the case, then du is going to be f of x dx. So it's not clear which of these substitutions we should do, but probably one of them. So honestly, you could just guess. There is a trick, there is a strategy for seeing what you're supposed to do, but I'm going to just sort of tell you the answer. And the answer is I'm going to let u be equal to f of x. So I'm not going to do this one. I'm going to do this one. And let me explain why. So if I take my integral here, maybe let me just even move that down a little bit so I can work on it. Where's my mouse? Why does it keep disappearing? So let's move that integral down. What I'm going to do is I'm going to write this as f of x to the 4, g of x squared, g of x dx. Okay? The dotted points and the endpoints are where f of x doesn't exist. Yes. Yeah. No, wait. The dotted points and the endpoints are is where the derivative is 0 and the endpoints. Yeah. Or sorry, just the function is 0. Like the derivative of capital G is 0, but that's the same thing as saying just where f is 0, right? So it's where f is 0. Okay, so I've written it like this, and you might be like, okay, well, why are you doing that? That's really weird. So the thing that occurs to me is I say, okay, if I'm going to make a substitution, I need a g of x dx hanging around, right? So I'm going to take one out, and I'm just going to put it to the side and be like, I'm going to use this for my substitution, so I'm just going to like keep this around. The other g of x's, I can get rid of using this, right? So using that identity, I can turn them into f's. So g of x is equal to what? F of x squared minus 1 squared g of x dx. And now if I apply my substitution, u to the 4, u squared minus 1 squared du. And this is a polynomial, so you can integrate it. Sure, same. So does that make sense? And the other substitution doesn't work. You're free to try it. But the other substitution doesn't work because if you have to take out an f of x in order to be able to do the substitution, you're left with an odd number of f of x's left over, right? You're left with 3 f of x's and then the f of x you need to do the substitution. The problem is that you can't get rid of the 3 f of x's. You can get rid of 2 of them, but you can't get rid of the third. So when I look at this expression, I say, right? There's an odd number of g's, which is exactly what I need to keep one for my substitution and then to convert the rest into f's. Okay, so that's sort of how you do this. And then you can integrate this problem just by expanding out this polynomial, right? You don't have to do any more integration techniques here. Expand this expression out, figure out what your answer is from there, and then you just get a polynomial and you can integrate it. Okay, how is f equal to 0 here? So I mean, like, this is the graph of f of x, right? So where is it 0? It's 0 where it touches the x-axis, right? This is the line x is equal to 0. Does that make sense? Well, these are just what are the endpoints, right? Whenever you check for maxima and minima, you have to check the endpoints as well. So these are just the 4 points you have to, or the 5 points that you have to check, right? How does this help us find maxima and minima? So maxima and minima have to occur at critical points, and these 3 are the critical points of G, right? So if a maxima or a minima occurs, it must be at one of the dots, either the endpoints or the critical points of the function capital G. And those are the, those 3 at 1/2, 2, and 4 are the critical points of capital G by the fundamental theorem of calculus, right? By this equation right here. No, at 1 and 3, those are critical points of F, and so potentially inflection points of G, right? Yeah. Last week, Ahmed. Last week we did a bunch of the chapter 8 exercises. Yeah, so if you pull those up, you should be able to find them. Next one. So a bunch of the week 8 poll questions. Let's see. So 2. Week 8 question 2, we have a poll video of. So person who asked me that, did you see the poll video or like the video for that one? Because we did that one in class for sure. We did 5 as well. Yeah, I'm pretty sure we did. Let me see if I can't hunt it down. Week 8. All right, let's see here. Yeah, so I have it up here for sure. Let me just try and find the place where I take it up. Yeah, so this is close enough. So here's question 2, then question 5 is E0 e to the x squared, is that one? Oh, I think I called this question. Okay, here, I think I call it question 4, but I'm pretty sure it is question 5. And then 18, I don't think I did 18 though. So let me look at 18. Oh, this is 18, right? Like this question isn't exactly problem 18, but it's basically 18. Right? So the poll question 18 is basically this problem, but just the graph is like flipped around a bit. So to find the global max and min, you just have to, for whatever reason, the poll problem is showing 2 correct answers, which is wrong. It shouldn't have 2 correct answers. But you know, you have to go through and you just have to literally compute. Oh, 15. Okay, sure. So I don't think we did that one. So this is so it says if f of x is x to 4 t squared plus 1 2021 dt, find the integral from 0 to 4 f of x dx, like that. See, Jack? All right, what do we want to do? What do we want to do? Yeah, how did we do this one again? I feel like we might have did this one by parts. So let's try it. So I want to try and integrate this by parts. So let's let u be f of x, dv be dx, du is f prime of x, dx, so that v is just x. Now, based off of this, f prime of x is equal to negative x squared plus 1 to the 2021. So if I do this by parts, what am I going to get? So I'm going to get the integral from 0 to 4 f of x dx. is uv, so it's going to be x, f of x from 0 to 4 minus the integral of v du. So that's x f prime of x dx from 0 to 4. So this is going to be 4 times f of 4 minus the integral from 0 to 4 x, f prime of x is, where did I just say? Oh, there it is. That's going to be plus x squared plus 1 to the 2021 dx. Now I can solve this with a substitution. So let's let u be x squared plus 1. So du is 2x dx. And so this becomes 4f of 4 plus 1/2. Well, here, let me write in the substitution first. So we're going to get 1 to 17 of 1/2 u to the 2021 du. So it's going to be 4f of 4 plus, so 2022, 1 over, what's 2022 times 2? 44? U to the 2022 from 1 to 17. So that's going to be 4 f of 4. We're going to have to figure out what f of 4 is here in a second. Plus 17 to the 2022 minus 1 divided by 44. Oh, and f of 4 is just 1, right? Yeah, f of 4 is 0. So this term is 0. So we get 17 to the 2022 minus 1 over 4044. Yeah, no problem, tutor. I'll see you later. Brandon, I mean, that's up to you. If you want to take a pass on that, you can. And that's the sort of freedom that you have if you do that. Alternatively, you can write it and then your lowest gets dropped, right? So your lowest gets dropped no matter what. If you skip this test, this is your lowest, so it'll get dropped. And especially if you've got other stuff to worry about, like other tests and stuff. But alternatively, if you write this test and you do great, then one of your other tests will be dropped, right? So it's up to you. You kind of have that freedom to make that choice. So yeah, this is a little bit tricky, Simon, because you might be like, how the heck would I know to integrate that by parts? And the thing that sort of occurs to me when I see this that makes me want to integrate by parts is to say, oh, okay, well, this is like the integral of an integral, right? Like that's sort of nasty. How the heck do I handle that? So when I see this, I say, okay, I kind of want to use f prime. Like if I can get f prime of x to show up, I sort of like get rid of that integral, right? So I'm thinking I want to use that. How do I get f prime to show up? Oh, okay, I need to differentiate f in the integral on the right. How do I make that happen? Integration by parts. So that's sort of how that occurs to me, but this is definitely a tricky question. This isn't easy at all. Okay, so that's definitely sort of like a tough one. And then let me see if I can't just grind out 8-1 really quickly. So right, exactly, yeah. And it's rare that will happen, that you have to use that hidden 1, but it does sometimes happen, right? Like this does sometimes happen where you have to do that, right? Just like when we did ln x and we integrated ln x, we had to do that sort of secret, 1 dx thing there, but it does sometimes happen. So if you find yourself completely and totally stuck, that's not a bad thing to try. No problem, Christian. Now for person who asked for 8.1, yeah, let's see if we can't do this pretty quick here. So for 8.1b, so we've got g of t is 1 plus t squared divided by root t. And the trick here is to sort of like split this one up, right? So let's write this as 1 over root t plus t over root t plus t squared over root t. And then let's just try and write this so that it's a power, right? So we get t to the negative 1/2. What is t over root t? So that's just t to the 1/2. And then this is t to the 3/2. Okay, and then antiderivatives tells us that the antiderivative of t to the n is 1 over n plus 1 t to the n plus 1, right? So in each of those cases, we're just going to let n be this exponent when we do this. So we're going to get, when we anti-differentiate this, which again, now we know, we didn't know this at the time, right? But that's what the integral sign means. So let me just use that. So t to the negative 1/2 plus t to the 1/2, that's a quarter, plus t to the 3/2. Okay, so if n is equal to negative 1/2, when I plug this in, I get negative 1/2 plus 1 t to the negative 1/2 plus 1, right? So that covers this one. Then let's do this one. So I'm going to get 1 over 1/2 plus 1 t to the 1/2 plus 1, right? So that's that one. And then t to the 3/2. Right, that's that one. Yeah, exactly. You know, this is sort of like the first antiderivative problem. Like, we didn't want to give you anything that required you using a secret rule. But sometimes, you know, the purpose of this question was for you to look at this and say, okay, I don't need to use any secret rule here if I recognize that I can sort of split this function up into its separate pieces. Do you know what I mean? Like, this was sort of the critical trick in order to be able to do this, because, you know, at this point we hadn't talked about, you know, parts or substitution or anything like that, right? It depends. What do you mean? Where would it, like, you know, if you have to use substitution or parts, that might be a thing that you have to use. But, you know, you don't try not to use those things if you don't have to, right? So if you can avoid using parts and substitution and can find an antiderivative directly, that is ideal. Yeah. And then, yeah, those are the only two other techniques we have, right? So we've got that table that I gave you of like the standard antiderivatives, and then substitution of parts. And yeah, you know, try to do it directly if possible, and then substitution of parts after that, right? No problem, Simon. See you later. And Z plus 1, you know, 8.1D, this is a little bit mean because, you know, this now is sort of a substitution trick, but the idea was for you to just say, okay, what do I know that differentiates to, like, the Z plus 1 is annoying, but if it was just Z, right, we know that would be ln of Z, you know, plus a constant, whatever. And then to realize that basically, if I just put Z plus 1 everywhere, it really doesn't change anything. Like, the chain rule acting on the Z plus 1 doesn't do anything. Yeah, wait, what part of that is bugging you? Right, because the derivative of ln Z is 1 over Z. Right, and so the exercise here was just to realize that taking like Z plus something really doesn't affect the derivative. Yeah, which of course we know a little bit, you know, we know a little bit more now that we've seen like substitution and stuff, but that was just sort of the lesson I wanted you to get when we first sort of did antiderivatives. That's what I wanted you to see. It's just that Z plus 1 doesn't do anything, right? And if it was Z plus 4, that doesn't change anything. You put Z plus 4 everywhere, right? So these like affine transformations or Z plus some constant really doesn't affect the antiderivative. And that's just a lesson to take from that. Okay, you're good? All right, everyone's happy. We ran a little bit over this time, but I mean, you know, my internet died, so I'm kind of happy to do that. Also, I ran out like 5 minutes early on Thursday because surprise Leaf tickets. So I don't mind going a little bit over today just to sort of make up for that. Hopefully that makes sense though. Everyone don't hesitate. Last tutorial, no, shouldn't be, not yet. Yeah, they should do tutorials right up into the last week. So tutorials up until April, whatever. So lots of stuff still, lots of stuff. See you, Aria. All right, everyone, I'm going to call it here. Got some stuff I got to take care of. But yeah, I'll see you all on Thursday. All right, so I'll see you then. Ciao.